please do take some time and do that homework, even if you are finding that everything is making sense and is working for you. Unlike a number of other things in terms of learning, math requires practice. It's not unlike learning a language or learning an instrument. You can understand it in theory all you want, but if you don't practice it, it's not going to come fluidly for you. So that's what the homework questions are for. And if you get to the end of the homework questions and you find you're still craving more practice, please send me a note and I will see what I can dig up for you in my tickle trunk of math problems. So this is directly from the lecture notes. If you have your own copies of this, you can follow along. I will be switching back and forth between sharing the screen and going back to the whiteboard to work some things through. But to start, let's take a look at this diagram. To introduce some common geometric notation, we are using the following diagram. So there's a whole bunch of lines here and all sorts of things going on. In mathematics, by convention, if we are using a capital letter, we are referring to an angle. Okay? If you see a lowercase letter, it will be referring to a side, and if you see a capital letter, it is referring to an angle. I try to be consistent with that throughout. That is the convention in most of mathematics. Unless it says otherwise, you can count on that pretty much being the case. The other thing that we start to note here is look at these little dashes that we do through here. If you see a line that's marked with a single dash and another line that's marked with a single dash, that's indicating that these lines are the same length. So here I have 2 dashes and 2 dashes, so that indicates that these longer lines are the same length. The shorter lines match, the longer lines match. That is not the same as these things, these arrowheads. These arrowheads are here to recognize that these lines are now parallel. So we're getting, if you see the arrows, that indicates that you have parallel lines. Parallel lines, the reason for noticing parallel lines, we'll talk a little bit later, talk about a little bit later in class, but that's what those are indicating. And then finally, you'll see these little symbols in the corners. If you see matching symbols in the corners of geometric shapes, that is to indicate that those angles are the same size. So in this particular drawing, angle B and angle C have the same size, whatever that size ends up being, and then angle D and angle A have the same size, whatever that ends up being. So that's a brief introduction to some of the notation that we use in geometry. The other thing that we take note is that we can use the letter names at the vertices to also refer to line segments. So if we, in the absence of lowercase letters, so as you see there is no lowercase letter on this bottom line, we can go ahead and use the vertices as a name for the line segment. So this corner, this vertex A and this one B are at either end of this line segment, so we could name this line segment AB. The same thing, of course, would happen at the top. We have a corner C, we have a corner D, so the line segment between them will simply be named CD. The other way that we can name angles is through 3 letters. So looking at this angle right here, we could just name this angle B, or if that wasn't clear enough for us, we could name this angle EBA because it goes that way, and the letter in the middle, of course, is the middle of the angle. Going the other way, we could go EAB as well, or go the opposite direction, BAE. All of these things are accurate ways to name these angles. The rest of this is starting to talk about these triangles. I'm going to zoom out so that we can see the words and we can see the diagram at the same time. So there we go. This drawing contains 2 triangles. To name them, I list the vertices as we go around the shape, either clockwise or counterclockwise. It doesn't really matter. You just pick a starting point and go from there. So this triangle down here can be named AEB with the 3 corners of that triangle. And then the triangle at the top could then be CED, again going around the triangle. We've already talked about the tick marks, and we've already talked about the rest of those symbols, so that lets us know that we are at the end of this page. Let's take a look now at these triangles. 2 triangles are said to be similar if all the angles of the first triangle are equal to all of the angles of the second triangle. However, since knowing two angles of a triangle automatically tells us the third, because the sum of the angles in a triangle is forever and always 180 degrees, we only really need to match 2 pairs of equal angles to decide if the triangles are similar. Because if 2 of the angles are equal, the third one must be equal. So if we take a look at these 2 triangles, again, we're dealing with these little symbols. I've got a star that matches with a star. I've got a little O that matches with another little O. Okay, so somewhere in here, it looks like these things match. Because we can see that these angles, we've got one angle they're calling BAC, so we follow it BAC, that's talking about this angle, is going to be matched with EDF, so again, we follow the letters EDF, that puts it with this angle. We can see that those match. Similarly, we can see that those match, so the 2 triangles are similar. The way that we write that is we literally write triangle ABC. We use this little symbol. It's called a tilde symbol. That's less important than recognizing that what it means is congruent to. Okay? So that symbol simply means is congruent to. So triangle ABC is congruent to triangle DEF. Because these 2 triangles are similar, the ratio of the corresponding sides are equivalent. That doesn't mean the sides are going to be the exact same size. It means that the ratio of the corresponding sides are going to be equivalent. So that ratio work that we started working on last week comes into play when we're playing with triangles this week. Here we find that the ratio of side AB to side BC to side CA is going to match with the ratio of side DE to side EF to side DF. Put a little bit more simply with fewer words, this 5 between the angles here is going to match with this X. This 8 is going to match with 10, and this 4 is going to match with Y in some way or another based on the ratios of the 3 sides. And we're going to take a look at that in just a moment. So this is where I'm going to flip over to the whiteboard. There are the triangles that we're talking about. Oh, let's get that focused just a little better. There we go. And here's how this is going to work out. We've got this ratio that we need to work with, 5 to 4 to 8. That's the order that I'm going to put it with. And it's going to be equivalent to the same things on this side, which in this case happens to be X to Y to 10. Now we can use this and we can do exactly what we were doing last week in terms of solving ratios. We can set these things up. I'm going to put X, Y, and 10 as the tops, so I'm going to get X over 5 is going to be equal to Y over 4, and then that's going to be equal to 8 over 10. There we've set the ratios up. I'm going to start just by solving these 2 simply because they're right next to each other and it makes my life easy. So Y over 4 equal to 8 over 10. I'm going to multiply by 4 on both sides to get Y on its own. That 4 will cancel. And then I can also do some reducing here. 2 divides both 4 and 10, so we're fine there. And then 8 times 2 tells us that Y is going to be equal to 16 over 5. Carrying on, I can do the same thing again to solve for X. So up here, I'm just going to go, I've got X over 5 is going to be equal to 8 over 10. Again, we'll multiply by 5 on both sides. 5's on this side cancel. 5 divides by 5, leaving us with 1. 10 divides by 5, leaving us with 2. And then this can simplify. 2 can go into 8 4 times. And that's how we solve those triangles. Oh, thank you, everybody. Yes. The reason that it's 8 over 10 instead of 10 over 8 is because I goofed and moved too quickly. Shall we back up and try that again the right way around? I should have looked up a little bit earlier. Sorry about that, folks. The math basically remains the same. It all just simplifies a little bit differently. So let's go through this just really quickly. So that should be 10 over 8. And that multiplies by 4. 4 goes into 8 twice, so that's fine like that. And then 2 can go into 10 5 times. So y would simply equal 5. Let's flip this one around and do the same thing again. Dun, dun, dun. This becomes 10 over 8. We've multiplied by 5 on both sides. This doesn't simplify. That's much better now. 5 times 10 gets us 50 over 8, but that will reduce both 50 and 8 divide by 2 very nicely, and we end up with 25 over 4. So, except for a small goof, that's how we do that. Which, if I had been following my own notes, would have popped out exactly the way we were expecting it to. X is 25 over 4, and y is equal to 5, which is what we're expecting it to be. Thank you for those of you who caught that. Thank you for asking. This is just a reminder that everybody does make errors in mathematics. This is why I like to see the process and not just the final answer, because silly things like this can happen. The Pythagorean theorem. This may bring back memories for those of you who've seen this before. If it's been a while, that's okay. This is one of those ones that'll come back to you. The Pythagorean theorem, named after that famous mathematician Pythagoras, says that in a right-angled triangle, the side length which is opposite the 90-degree angle is called the hypotenuse. And if a right-angled triangle has lengths A, B, and C, C is the length of the hypotenuse, and that tells us that the relationship between these things comes out like this. A squared plus B squared equals C squared. This is important. We can only apply the Pythagorean theorem if we know that a triangle is a right triangle. If it doesn't have a 90-degree angle in it, we cannot use this theorem. We can only use this theorem on triangles with 90-degree angles. Fortunately, we have one right here. So let's take a look at this one. We have side lengths 8, 12, and 1/3 unknown side. That little box in the corner lets us know that we're dealing with a right angle triangle. That means 90 degrees. The sides we're given are 8 and 12. 12 is opposite our 90 degrees. That's what I mean by opposite. Okay, so that means that this must be the hypotenuse. Our Pythagorean theorem, a squared plus b squared equals c squared. The hypotenuse is by convention always c. The other two sides, it doesn't matter. We can interchange them. In this case, I'm going to make that a, and I'm going to make this b. So following along that same pattern from the Pythagorean theorem, that's going to tell us that 8 squared plus b squared will equal 12 squared, which just means that that's 64 plus b squared equals 144. We subtract 64 from both sides. And that tells us that b squared is equal to 80. Have I done that math correctly? Pretty sure. Yep. So we'll take the square root on both sides of that. The square root cancels out the squares. Trust me on that one. We'll talk about more of that when we get to that portion of the course. but that essentially means that b is equal to the square root of 80, or approximately 8.94. Wherever you see these little squiggly equal signs, all that means is approximately. It means that we're not getting it exactly accurate. It just means approximately. This is the most accurate answer. By the time we hit about midway through this course, I think, we'll be working with numbers under the radical, and we'll be able to be comfortably using those and manipulating those, and that's ultimately how we're going to want the answer. Until we get to that time, though, this will do just fine as an approximate answer. Okay, really quickly, everybody with me so far? Just waiting for a couple more responses. Just 2 more responses and then we'll move on. Okay, most everybody's with us. There are some questions that some people have that they'd like to ask me later. I'm certainly happy to answer those questions a little bit later. Moving on, angles. As I talked about earlier, whenever you've got a triangle, you're going to have angles. I'm going to use capital letters here. I forgot to in my notes, but in this case I will, just to make it clear. The angles of a triangle, angle A plus angle B plus angle C, must always add up to 180 degrees. Doesn't matter what triangle, doesn't have to be a right angle triangle. Every triangle, as long as it's on a flat plane, will have angles adding up to 180 degrees. Interestingly, it's the exact same thing with a straight line. A straight line also kind of represents half a circle. If I was trying to draw the angle of this line, I could draw an angle marker like that, which looks exactly like half a circle. And if we do that, half a circle is, of course, 180 degrees. The reason that this becomes important is because if we had some line that was coming in onto this flat line that we've got, let's go with this one. Say I had something that goes in like that. Well, I immediately know, and I will do this with some colors just to make it clear, that part of the angle and that part of the angle have to add up to 180 degrees. And that's something that becomes very, very useful when we're starting to work out some problems. Okay, so if I had this angle here as A, and I had this angle over here as B, we could just go ahead and say that in this case, A plus B would have to be 180 degrees. This helps us do a number of interesting and fun little things with angles. And I'm just going to keep moving through all this. So there's a couple of theorems. Now, as I go through these theorems, they are in the notes and you will be able to refer back to them. But these are things that for those of you who are building your formula sheet for the tests, this is one of those things that might be useful to have on there in some way, shape, or form. If we have some parallel lines, and I'll throw those on there so that we can indicate that they're parallel, and then we have some line that passes through it like that. There's a bunch of stuff that we can know about this. all based on a couple of very, very simple ideas. First thing that we know is that this angle here and the one on its exact opposite side, this one here, those things have to add up to 180 degrees. That's what we just looked at. Now, what's very interesting is, and I think I've got these out of order in the notes, but that's okay. We're going to carry on this way. Angles that are opposite each other in crossed lines are exactly the same. Okay, so this angle in here and this angle in here, both of them marked in blue, are going to be the same size. The greens, obviously, the same thing ends up happening there. And we end up with those being the same size. Now, there's a couple of other fun things that end up coming up out of this. One of the things that we can do is we can start to draw shapes in here and also be able to see how these angles work out. So one of the ones that we do is called the parallel line theorem Z pattern. And in this case, I'm just going to draw over this. I hope this doesn't smudge things too badly. But if we can look for a Z forwards or backwards, like that, we discover that the angle in there and the angle in there are exactly the same. Okay, so that becomes our parallel line theorem Z pattern. And it's called a Z pattern, obviously, because we can make a Z. You could also think of it as an S pattern. You can go backwards the other way. So if I went this way, let's make this with a little cleaner with some other lines. Again, if we have some parallel lines, and a line passing through it, we can also create an F pattern, forwards or backwards. And that tells us also that we can create some angles that we know are going to be the same. So in this case, that angle and that angle are going to be the same. Oh, somebody's unmuted. Oh, there we go. Okay, so that's the Z pattern. That's the F pattern. And then we have the C pattern, which some of you may already have figured out by just looking at all of this. So again, parallel lines, a line passing through them. We can recognize that there's a letter C in here, like that. And what that one is telling us is much like our flat line, we get certain things that add up to 180 degrees. So here we're going to get a B and an A. And in this case, they add up to 180 degrees. And then finally, as I started mentioning at the beginning, but I will go ahead and make just a little bit more explicitly clear here again, when we get two lines that cross like this, the angles opposite each other are always equal. So if we go ahead and rename these as A, B, C, and D, we can say that A will equal B and C will equal D. So with all of that information, we can go ahead and work on a problem. And we can start to figure out all sorts of angles with very, very limited amounts of information. So let's take a look at a problem and work our way through it. Here we have some parallel lines. We have this great big huge line that comes all the way through it. Down at the bottom it makes a check mark, and in making that check mark, of course, we end up creating a triangle. We've got a bunch of missing pieces that we're going to try and figure out here. That should be a C, pardon me. There we go. Okay, and then a couple of pieces of information we have been given. This angle right here is 130 degrees. This angle out here is 110 degrees. Immediately there's some stuff that we can figure out. Flat lines don't just go left and right, they can go up and down too. So when we look at this, we can see that we have a flat line going this way. We know one side of the flat line is 30 degrees, which means that we can immediately determine the other side of our line because it has to make up 180 degrees. A is going to be equal to 50 degrees because 50 plus 130 equals 180. As soon as I do that, I can take a look and I'm going to see my Z pattern is right there, which means that I can jump to the answer for E right away. Because I have that Z pattern, I know that E must also be equal to 50 degrees. Carrying on, looking at the easy ones to just pop out. Here, once again, I have a flat line. On one side of it, I have 110. I know I need to get to 180. So B must be equal to 70 degrees because, again, that gets us our 180. One more one that jumps out at us very quickly. I have angles that are opposite each other from crossed lines. That means that D must be equal to E, which must be equal to 50 degrees. That leaves us just one angle left to figure out, and that's C. Well, C is inside a triangle, and I already know two angles of that triangle, and I know that triangles must be equal to 180 degrees. So I can say that 180 degrees is going to be equal to whatever C is, plus my 70, plus my 50. We do just a quick little bit of arithmetic to figure this out. I'll subtract 120 from both sides, and that tells me that C is equal to 60. Wasn't that fun?
Sorry.
Okay. So that's everything that I need to show you on angles. With all of those little tricks, you should be able to handle all of the angle stuff that we throw at you. I will hold on just a minute, give everybody a chance to finish copying stuff down, and then we will move on to perimeter, area, and volume. Just about another 15 seconds, and then I'll move on. Okay, we'll keep moving. For those of you who haven't had a chance to copy all of this stuff down, or if it feels like it's going just a little bit quickly, if all goes well, we should have a video posted of this sometime tomorrow, so you'll be able to go back and review it. Okay. Perimeter, area, and volume. When we're talking about perimeter, we're always simply talking about the length around the outside of some object. So if I had some object, doesn't even have to be regularly shaped. Let's say it looked like that. An off-kilter staircase of some sort. If we were looking for the perimeter of this shape, I would literally be looking to try and add up the length of that side, and the length of that side, and the length of that side, the length of that side, these little pieces here. Add all of those pieces up, and you would have the perimeter. When we're dealing with perimeter, we just deal with units in one dimension. I know that seems like a strange statement to make, but it'll make more sense in a minute. Our units are in one dimension. Okay? Which means that if you had units and they had some sort of symbol on them, the generic symbol for units, of course, is just the letter U. There would be no power on there. I'm going to do this in a different color. It'll make sense in a minute or so why I'm doing it, but we can think of the units as U to the power of 1. When we're looking at area, we're looking at something different. We want to look at how much an object covers. Okay. Traditionally, when we're first looking at area, we like to look at squares and rectangles just because they're easy to visualize. Okay. So if I had this, if I had a length on this side, and I'll call this length A, and I had a length on this side, and I'll call this length B, the area of this square would be A times B, or simply AB, and the units in this case are going to be squared. So now our units are in 2 dimensions. Okay. We're taking up space now, so we are in 2 dimensions. Which then moves us on to volume. When we're looking at volume, we're looking at how much space an object takes up. So now we're looking at objects in 3 dimensions. So if I had A, B, and C, the volume of this object would be A, B, and C multiplied together, and our units in this case are now moving into 3 dimensions, which means that the exponent on it, the little number up top, is going to be a 3. Now, having done all of that, you can see now why I might have put a 1 up here. Most of the time, the 1 doesn't actually get written. It's usually quite invisible. So we'll just make that one disappear now. But it was there just so that you could see if you don't have an exponent there, it's implied that it's a 1. After that, we actually have to expressly put in our exponents. So in this case, our units will be squared, or 2 dimensions to the power of 2. And in case of volume, it'll be cubed raised to the 3rd power. So, that having been stated, let's take a look at some common formulas for some common shapes that you are going to be expected to know. We'll start with one of the nice ones, a rectangle. With a rectangle, you're going to get opposite sides that are going to be the same length. And there are 2 things that we're looking at with rectangle. We can look at the perimeter of the rectangle, which is to say the area or the length around the outside. And if I call one side of this the length, the other side the width, our perimeter is going to be 2 lengths plus 2 widths. 1 length, 2 lengths, so we have 2 of those. 1 width, 2 widths, 2 of those. Add that all up, and you have the perimeter of your rectangle. Area, on the other hand, is going to be taking these sides and multiplying them together. Okay, so our area in this case is going to be length times width. And that's it, that's all. Makes it very, very simple. Very, very similarly, we can go along and we can look at a very special case of a rectangle, which in this case is going to be a square. What makes a square unique in the world of rectangles is that all 4 of their sides are exactly the same. So not one of them is going to be the length or the width. We'll just call them all S for side. The perimeter of a square is just 4 times the length of the side, because there are 4 sides. And the area is going to be the side times the side, also known as the sides squared. And that's why we call it squared. That's where the term comes from, is from that shape of the square. Side times side gets us side squared. We'll keep moving with familiar objects. Let's take a look at the triangle. So I've put in here just a little dotted line, and that line takes us from the top of the triangle to the bottom of the triangle and indicates its height, which I will indicate with the letter H here. And then across the bottom, the length from one edge or one corner of this triangle to the other corner across there is called the base. So we represent that with the letter B. To figure out the perimeter of a triangle, it's always going to be different. You literally just add up the lengths of the outside. So if this had sides A, B, and C, you would add up A, B, and C. But in this case, we're more interested in the area of this triangle. The formula for the area of a triangle, we take the base of the triangle, we multiply it by its height, and then we take simply half of it. So it gets written out like this, is 1/2 base times height. Okay, one more two-dimensional shape to look at, and then we'll look at a couple of three-dimensional shapes. The last two-dimensional shape to take a look at is the circle. There are some pieces of the circle that we need to recognize. The very first one that we need to take a look at is what happens when we move from the center to the edge of the circle. The length from the center of a circle to its edge we represent for the letter R, and R means radius. There's another line that we deal with in circles quite often, and that's going from one edge of the circle to the other, passing through the center. That one we represent with the letter D. The D is equal to your diameter. The relationship between your diameter and your radius is simply that your diameter is equal to 2 of your radiuses, or radii. When we talk about perimeter on a circle, we use a special word. The perimeter of a circle is called the circumference, which I actually have to look at to spell and have had to do my entire life. I don't know why it's never stuck. There we go. Circumference. One of the lesser known knights of the round table. And the formula for the circumference of a circle is written two ways. One of them is 2 pi r, where pi for the time being is simply a button on your calculator, or if you don't have a calculator, you can approximate it as the number 3.14. I'll talk more about pi in just a moment. The other way that the circumference can be written, if we notice that we can replace 2r with the letter d, circumference is sometimes written as pi times diameter, or pi d. They're the exact same thing in the end, okay, because of this relationship here. But you can use either one. If you know your diameter already, you can just go ahead and use the diameter. If you just have the radius, multiply the radius by 2, then multiply it by pi. You'll get the same answer every time. Now, the same is not quite true when we're talking about the area of a circle. The area of a circle is represented by the formula pi r squared. So in this case, we're going to take pi, 3.14, we'll multiply it times r, and then we'll multiply it times r again. Has to be radius in this case, cannot be diameter. Forever and always radius when dealing with area. Pi, this is our first irrational number that we've been dealing with. An irrational number, for those of you who are keeping track of these things, is a number with a decimal that goes on forever without repeating. Last week we were talking about repeating decimals. In this case we have a decimal that does not repeat but still continues on forever, which is why we simply approximate it to 3.14. Pi has a long and interesting history. If we have time at the end of a lecture at some point later in the summer, I will talk a little bit more about it. But it is supposed to represent the relationship between, or the ratio between, a circumference and its diameter. Okay, so whatever the perimeter of your circle is, whatever the circumference of that is, if you divide it by the diameter and you have both of those measurements accurately, you would create pi. And that's how pi comes about. Okay, so these are good formulas for your formula sheet. And we're going to move on to 2 three-dimensional shapes that we need to be familiar with. While we're looking at pi and circles, we'll move on to the first of those three-dimensional shapes. I think I can squeeze it in here without having to move anything. Let's do it like this. We're going to make a circle three-dimensional, and we end up with a sphere. You are not responsible for the surface area of a sphere. We're only responsible for the volume of a sphere. So the formula for the volume of a sphere, again, where the radius goes from the center to the edge, is a funny little formula. 4/3 pi r cubed. So there's the formula for the volume of a sphere, 4/3 pi r cubed. Okay, one last object to take a look at. Excuse me as I clean this up. Rectangular boxes, sometimes known as rectangular prisms, sometimes just known as boxes. Dun, dun, dun. Let's do that. That comes down like that, goes across like that, and then we'll make this three-dimensional. If that's the length, and that's the width, and that's the height, your volume for any of these rectangular boxes is just going to be length times width times height. Okay, and with that, we have a whole bunch of information, and we haven't done too many examples of what we're going to do with this information. So, having provided all of this information, let's go through one worked example, then we'll take a brief break, and then we'll go through questions on all of this. So, for those of you looking to yawn and stretch, bear with me just another couple of minutes, and then we will have time for a break. Here we have some rectangle. And on this rectangle, we have the shorter side that measures 3 centimeters, and we have a diagonal on this thing, which is going to measure 9 centimeters. That's a 9, not an A. It's a rectangle, so we know that the corners are going to be 90 degrees. And also because it's a rectangle, I know that the opposite sides are the same length. Okay. And the question, of course, is going to be, well, what is this missing side? I'm going to represent this side. I represent it in the notes with an L, but my L's look very much like ones, so for clarity, I'm going to call this side B. Okay, and we want to find the length of B. So, looking at this, we notice that, of course, as soon as we draw a diagonal across this rectangle, it creates for us a triangle. So we're going to use the properties of a triangle to figure out B. We're going to use the Pythagorean theorem in this case. So, a reminder that our Pythagorean theorem is simply a squared plus b squared equals c squared. In this case, 3 represents my a, so I'm going to get 3 squared plus b squared, and 9 represents my c, so I'm going to have 9 squared there. Doing that actual squaring out, I'm going to get 9 plus b squared equals 81 squared. I'll subtract 9, not squared, sorry, equals 81. I'll subtract 9 from both sides. And when I do that, I discover that b squared is going to be equal to 72. Because b squared is equal to 72, I'll know that b is equal to the square root of 72. And if you plug the square root of 72 into a calculator, it will tell you that it is worth approximately 8.5. I'm going to go ahead and use that 8.5 number for the rest of this just to make life easy. But that is what we're looking for to start with here. So this is going to be equal to 8.5 centimeters. Now that I have that, I say to myself, oh, now that I've got all of these numbers, I'm kind of curious. What is the perimeter of this box? So the perimeter is equal to 2 of our lengths plus 2 of our widths, which in this case is going to be 2 times 3 and 2 times 8.5, which is 6 plus 17, or approximately 23 centimeters, with a little invisible 1. Having done that, I can also take the moment and figure out the area. And the area, of course, is going to be the length times the width, which in this case is going to be 3 times 8.5, which is going to get us approximately 25.5 centimeters. And in this case, I put a little squared on that centimeters because we're dealing with area. And with that, we come to the end of the formal lecture section on geometry. Whew, that was a bit of a marathon run. Thank you all for bearing with me. We'll stop now just for a moment. If people want to start asking me a few questions, that's great. If people would like to take a couple of minutes to yawn, stretch, stand up, get away from their screen for 5 minutes, I will restart formally at 5:35. So you have 5 minutes if you need it. So go get yourself a glass of water, step away from your screen, look outside, stretch your eyes, all of those good things. Okay, we just have another short few seconds and we'll get things started again. Okay, just to make sure that we've got everybody back, we'll do one of these polls again really quick. Is everybody back and ready to start again? Just waiting for responses from a couple more people. Okay, I'm assuming those people aren't quite back at their desks yet. Just 3 people missing, so hopefully they will catch up. But we will keep going so that we don't run out of time. Okay, I would like to do a few problem questions in geometry, zipping through here and taking a look at a whole bunch of these different types of questions so that everybody gets a chance to see this stuff at work. But a lot of this stuff also draws on what we were doing last week, and I had a couple of people who were asking me to go through some questions in the fractions homework, specifically looking at these ratios. A number of people were having questions with ratios, particularly regarding ratios with fractions, which I thought, oh, that's an excellent idea. Let's take a look at a couple of those. Because this is going to be very much the sort of work, particularly when we get down to questions 13, that we're going to be doing when we solve the geometry work. So if we can do this work with the ratios here, we'll be able to apply that exact same learning to solving our geometry questions. So I'm going to start off by taking a look at question 12B and 12C. Okay, I'm going to do these 2 questions out. And then I'm going to go on to do 13, A, B, and C. Okay? I need to switch back over here. Oops. Try that again. There we go. That's what I'm trying to do. Okay. So, question 12B asks us about to solve the equivalent ratio 1 to 2/3 and x to 4/5. Question 12C, and I'm just going to write it down here so I don't lose it. It's going to be 1/3 to 2/7, matching with 5 to x. So we take a little look at the first one, and as we learned last time, if we have ratios A and to B and the other ratio C to D, we can set this up as equivalent fractions A over C equal to B over D. Or we could flip it on its head and that would work fine. Whichever way is most convenient. We're going to keep it this way for the time being because it keeps the x on top. Sorry, it keeps the x on the bottom as I look at it. Sorry, I'm actually going to flip this over. What I'm going to end up doing the way this is asking for it right now, it would say that this is 1 over x would be equal to 2/3 over 4/5. What I'm going to do to make my life easy is I'm going to take this whole thing and I'm going to flip it over, okay? Because it means the exact same thing. So I end up with x over 1 is going to be equal to 4/5 over 2/3, okay? Now, in this particular case, the reason that I've done this is because any number over 1 is just itself. Okay, so I can immediately simplify my left-hand side down to just x. And then we have to take a look at the right-hand side. Now, when we're dealing with fractions like this, we have to remember what this line says. This is another way of writing a division question. So, we could rewrite this as 4/5 divided by 2/3. As we were learning last week, when we're dividing fractions, we actually flip that second fraction and multiply. So this becomes 4/5 times 3 over 2. When we turn something into a multiplication question, we always want to pause and see if there's anything we can simplify before doing our multiplication. And in this case, there is. 2 divides both 2 and 4. So that can go down to a 1, and that can go down to a 2. And then I can go ahead and multiply these. 2 times 3 is 6. 5 times 1 is 5. So x is going to be 6 over 5. It doesn't always work out so nicely that x is going to be over 1 or that our unknown is going to simplify that easily. So we'll take a look at the next question. We can see the patterns are going to be similar, but the math is going to be just a little bit, there's going to be one extra step in the math to make it all work out for us. Okay, so I'm just going to draw this line all the way down here so we can see the work on either side. I'm going to get 1/3 over 5 is going to be equal to 2/7 over x. Again, I take a look at this. My x is on the bottom. That's not convenient for me. My life is actually much easier when my unknown element is on top, so I'm going to flip these over. And I'm going to end up with 5 on top over here and 1/3 on the bottom. And I'm going to end up with x on the top over here and 2/7 on the bottom. At this point, we don't really want to start thinking of things in terms of fractions. The first thing we want to do is get x entirely by itself. X is being divided by 2/7 right now. We undo division by multiplying, and we multiply by the exact same thing it's being divided by. So I'm going to multiply this by 2/7. And whatever I do to one side of an equation, I must do to the other to keep it balanced. So this side is also going to multiply by 2/7. These will cancel out. I'll have x by itself. But on this side, it looks a little bit different. So what I actually have to do is I have to do this multiplication first. So I need to go 5 times 2/7. And when I do that, I end up with 10/7 on top and still 1/3 on the bottom. But now it's all just equal to x. Now that I've hit this point, I've actually hit the exact same point that I hit over here. Okay, which means that we can, the same way we did over here, turn this into a division question. So x is going to be equal to 10/7 divided by 1/3, which is to say that's going to be 10/7 times 3 over 1. Now that we've hit the multiplication point, we check to see if there's anything we can do to make this simpler. In this case, there isn't. So we go ahead and just multiply straight across. 10 times 3 is 30. 7 times 1 is 7. And that ends up being our final answer. I have a question about why the multiplication is happening. So you want to know why it's being multiplied? Oh, this is actually being multiplied on top. This, you can think of this as over 1. Okay, it is being multiplied on top, and the reason it's being multiplied on top is so that those things cancel. Is that the question that you're asking? Have I got that correct, James? Yeah, so it ends up being multiplied on top on both sides. I hope that answers that question. I'm also being asked, why wasn't the denominator also being multiplied by 2/7? In this case, the reason we're not multiplying by, oh, you get it now. Yes, we have to multiply it on top in order to make it disappear. When we multiply it on top and bottom, all we're trying to do is change the form that it's in. In this case, we're actually trying to move the numbers, so that's why we multiply on top on both sides. I'm making a whole bunch of hand gestures, but I just realized you guys can't actually see them. So, good. Good. Okay. This is the basic process. I'm going to take a look at a few more examples with this. Now we're going to be getting into stuff that's going to start to look much more like the geometry questions end up looking. Let me just pull up these questions again. So I'm going to do 13, start with 13A from the homework set in fractions. So this is question 13A, and it is asking 1 to 3 to x and y to 5 to 2. The first thing I'm going to do is I'm going to put all of these things into equivalent fractions just so that we can see where all of the pieces are. So this ends up being rewritten as 1 over y would be equal to 3 over 5, which is equal to x over 2. I'm going to start by just solving this pair over here. So I'm going to solve for x first, largely because x is already on top and it makes my life easy. So part 1 that I'm going to do simply says 3 over 5 is equal to x over 2. Same way we did in the previous questions, we want to get x on its own. It's being divided by 2, so I'm going to multiply it by 2. And just for clarity, I'm going to call that 2 over 1 so that everybody can see what I'm doing. And whatever we do to one side of an equation, we must do to the other. So I will multiply this by 2 over 1. And when I do that, these 2's cancel, and I'm just left with x on the right-hand side. On this side, when I actually do the multiplication, I'm going to go 2 times 3, and that gets me 6. I go 1 times 5, that gets me 5. And we're done. And that's how we get an answer for x. Now I'm going to do the second part. I'm going to do this 3 over 5 equivalent to 1 over y thing. And as I was doing in the previous questions, whenever I have my unknown element on the bottom, I'm going to take a moment and I'm going to flip it over to put it on top because it'll make my life easier. So in this case, I end up with 5 over 3 is equal to y over 1. And I all of a sudden realize that we're done. And the reason that we're done is because anything divided by 1 is just itself. So we can just rewrite this as y being equal to 5 over 3. And we've hit the end of our process. Now, it doesn't always work out that nicely for us. As I've said before, sometimes we get things that are slightly more involved. So if I go ahead and I go on to question 13b, I'm just going to make a little bit of room here. 13b is giving us, let me write down b, x to 1/3 to y, and then the other ratio is 3 to 7 to 1/4. As I did in the first case, I'm going to write out all of the equivalent fractions just so that I can see them all laid out. So I'm going to get x over 3 is going to be equal to 1/3 over 7, which is going to be equal to y over 1/4. The fraction in the middle is once again my complete fraction, so that's what I'm going to use, and I will solve for x first. So x over 3 equal to 1/3 over 7. In order to get x on its own, I need to multiply it by 3. So I'll go with that 3 over 1 on this side, and I'll do it again over here. And when I do that, 3's cancel on this side, leaving me with just x. And on this side, I get 1/3 times 3. Now that's quite fortunate. Somebody was very nice when they set up this question. 1/3 times 3 is 3/3. Do a little sidebar over here. 1/3 times 3 is equal to 3/3. And 3/3 is the same as saying 1. So what I end up with in the end here is actually just 1 over 7. And that's that finished. Then we go on to do the other equivalent fraction. So 1/3 over 7 is equal to y over 1/4. I want to get rid of that 1/4 on the bottom, so I'm going to multiply by 1/4 over 1 on this side, and we do the same thing over here. It's a little small, but trust me, that says 1/4 over 1. And when we do that, of course, on the right-hand side, our 1/4s cancel out, and we're just left with y. On our left-hand side, though, I have 1/4 times 1/3, which gives me 1/12, and it's being divided by 7. Well, 1/12 divided by 7 is not particularly easy for us to deal with. So I'm going to rewrite this as a division question, and just so that we can see how this mathematics works out. So that says it's 1/12 divided by 7, which is the same thing as saying 1/12 divided by 7 over 1. And sorry, as I'm pausing here, I'm suddenly just wanting to make sure that I've got all this written down correctly. Yes, good. Which then gives us 1/12 times 1 over 7, which gets us 1 over 84. And that 1 over 84 is our final answer. So, just before I go on to the geometry thing, does anybody need to see another one of these done out? Or are we happy to just move on to the geometry questions? Oh, we're at 50-50 right now, so if you have an opinion on this, go ahead and chime in. Okay, we're pretty close to the lines. So I'm going to do one more, and then we're going to see how this applies in geometry. Thanks, everybody. I've had a request to take a look at 14C, and I always enjoy taking requests. So let's take a look at question 14C. Okay, so this is a slightly different application of ratios, but it's the same idea. So this is 14C. It's asking us to divide the following wholes according to the given ratios. So in this case, we have the number 260 in a ratio of, oh yes, this question, haha, 2/3 to 1/5. I've heard your question, Allison. I'm going to go and do a little bit of geometry after this question, just to make sure that I cover that, because I'm cognizant of our time. And then, yes, I hear your question, and I'll come back and I'll do that. Okay, so very first thing that we need to do here is figure out actually how many pieces we have. This whole thing works out a little bit differently than a number of the other questions that are like this because we're dealing with fractions. But the easiest thing to do is to start off looking at equivalent fractions. Okay? So when we take this idea of looking at our 2/3 to 1/5 ratio, I'm not dealing with pieces of equal sizes, so it's a little bit difficult to see what's going on. So the first thing I'm going to do is turn these into equivalent fractions. So that means I'm going to multiply this fraction by 3/3, and I'm going to multiply this fraction by 5/5, and that gives us something that we can look at that's equivalent. And I end up with 10/15 to 3/15. Okay. Having done that, I can do one more tricky little thing here to make our life even easier. This looks like it's cheating, but this is how it goes. I have 15 on the bottom on both sides. So if I multiply the top on both sides by 15, which is to say whatever I do to one side, I also do to the other, all those 15s disappear, and I'm left with a nice little ratio of 10/3. And if I have a ratio of 10/3, then what that's telling me is I have 10 plus 3 parts for a total of 13 parts. I then take my original number, which is 260. I'm going to divide it by the 13 parts that are there, and it tells me that each part is worth 20. So that's supposed to be an E, each part contains 20 pieces. Now, if each part contains 20 pieces, I now know what I can do with all of these. I can go ahead and I can multiply it by my 20 pieces, and it should show up the way it's supposed to. Just one quick second to check my notes to make sure I'm not leading you all astray. Good. Okay. Just make sure I'm doing this right. Okay. Oh dear. Sorry, 1 second. My mind just went blank on me. Oh, sorry. That's what I'm doing. That's why my mind went blank. So where we end up going back to is we actually end up going back to this. Because this is ultimately equivalent to this. This is the one we end up wanting to use because it's much simpler numbers. It's equivalent to this ratio. Because it's equivalent to this ratio, we can just go ahead and use this. So taking that and applying it to my 20 pieces, on one side, I'm going to get 10 times 20. On the other side, I'm going to get 3 times 20. And then those end up being my pieces. So 260 in a 2/3 to 1/5 ratio ends up being 200 to 60. So just for clarity, based on the question that I've just seen pop up, this 10 is there, this 3 is here, and the 20 comes from the number of pieces that we've put together. I will go over another one like this if I have time towards the end. I'm just watching the time that I've got, and I need to move on to a couple of these geometry problems for people. Now, that being said, a lot of you, when you did the pretest, did very, very well. I'm very pleased to see that. But for those people who haven't had a chance to do that, I'd like to take a look at just a couple of questions. That's the geometry pretest. That's not the one I'm looking for. Okay, here we go. So let's start off with question number 1. Given the following congruent triangles, find the lengths of the missing sides. This ends up being exactly like the ratio question that we were dealing with before. Let me just draw out these triangles really quickly so that we can see them. With a 3, 4, 6, 0, and a star. Star, 0, X. There are those triangles. First thing we note is that if we take this triangle and we rotate it 90 degrees, it matches up here. So if I have a ratio of 3 to 6 to 4, and I watch how it matches my other triangle, that's going to match with the ratio 1 to y to x. And then I turn those into equivalent fractions, and I end up with 3 over 1 will be equal to 6 over y, which is equal to 4 over x. And then we carry on exactly the same way that we do with any of our other ratios. I'm going to take my 3 over 1, and I'll solve for x first. So I'll put this with x over 4. I'm going to make my life easier and flip these over. So I'm going to get 1 over 3 is x over 4. We multiply by 4 on both sides. And it tells us that 4/3 is equal to x. One more time for the y. 3 over 1 is equal to 6 over y. Again, I'm going to flip this on its head. I'll get 1 over 3 rather, is equal to y over 6. I would like y to be on its own, so I'm going to multiply by 6 on both sides. The 6 disappears. I end up with 6 over 3 equals y. Well, 3 goes into 6 nicely. It goes in 2 times. So it turns out that y is equal to 2. Now, for those of you who are wondering, and I'm sure that there are a couple of you who are, if you would notice that turning a 3 into a 6 happens simply by multiplying by 2, and that if we then multiply 2 times 1, we actually end up with our answer. If you can sort of spot that happening, that's perfectly fine. You can sometimes jump to your answer by noticing that that's how things work. Just make sure that when you're doing it correctly, and what I mean by that is if we notice that we have to multiply by 2 to get there, whatever you do to the top of a fraction, you can also do to the bottom, and you can jump to your answer like that. I'd like to do 1 or 2 of these word problems so that people get a chance to see how those go out. So let's take a look at question number 5. I am 1.78 meters tall, or 178 centimeters tall. I go outside and notice that my shadow measures 0.5 meters. A tree has a shadow that measures 1.3 meters. How tall is the tree? So we take a look at this information, and we're going to put it into something that looks mathematical. And I can do a ratio of my height to the length of my shadow. I'm going to write that out. Height to shadow. And the reason that I'm writing it out like that is so that we're doing the exact same thing with our other ratio. We have some trees. We don't know the height of it. So I'll call it T because I don't know what it is. But I know its shadow length is 1.3 meters. So I have to make sure that the shadow length are both on the left hand, or the right hand side rather, so that our actual heights are on the left hand side. Now I've got equivalent ratios and I can set up my equivalent fractions. So this says then I have 1.78 over T, and this is going to be equal to 0.5 over 1.3. As always, my unknown is on the bottom, so I'll flip it to make my life easier. T over 1.78 will be equal to 1.3 over 0.5. I'll multiply by 1.78 on both sides. And this disappears over here. So then the height of my tree will be equal to 1.3 times 1.78, and the result of that needs to be divided by 0.5. That's work for a calculator, so you pull out your handy-dandy calculator. And it gives us an answer of T is equal to 4.628. Most of the time we're being asked for answers to 1 decimal place, so we can say that T is equal to approximately 4.6. So, just to recap, the big and important part when you're trying to work out the word problems is making sure that you're identifying where your pieces are going in your ratio. And whichever order you set up your first ratio in, you have to set up your equivalent ratios the same order. As long as you're keeping that up and keeping that straight, everything else should work fairly straightforward. I'm going to go on to now question number 13. We're going to take a look at a circle. For those of you who don't have access to that, let me share the screen here so that you can at least see the question first. The area enclosed by half a circle is 8 pi centimeters squared. What is the perimeter of this half circle? Give both the exact answer and the approximate answer rounded to 2 decimal places. So what do I mean by all that? Area enclosed by half a circle is equal to 8 pi centimeters squared. So, what is the perimeter of this half circle at 8 pi centimeters squared? We know that the area of the circle is pi r squared. We're also being told that the area of this half circle, I want to make sure this, so half circle is equal to 8 pi. We want to do something to make these match. Okay, this is only half the area of that. So what I'm actually going to do is I'm going to take this area equation, I'm going to divide it in half. So what's that going to look like? That's going to say that it's going to end up being pi times r squared over 2, because I just want half of it, so I am dividing it by 2. I then take this and I set it equal to my 8 pi, and I can see that I have pi r squared over 2. I have 8 pi. Well, the pi's in this case can just cancel each other out. If I have pi on one side and pi on the other, I can make those pi's just disappear. So that tells me that my r squared over 2 is going to be equal to 8. I just want to find out what that r is, so I'm going to multiply by 2 on both sides to get rid of that 2 on the bottom. And it goes away like that. 2 times 8 gets me 16. I don't want r squared. In the end, I just want r, so I'm going to take the square root on both sides. Square root and the squared cancel each other out. And the square root of 16 is 4. So in this case, my approximate answer and my exact answer happen to be the same. And I can use this to form my perimeter. Now, remembering that the perimeter in the case of a circle is called circumference, and that our formula for that is 2 pi r. My r in this case is 4, so my circumference is going to be 2 times pi times 4. 2 times 4 happens to be 8. So I end up with 8 pi. But that would be, again, we're dealing with the whole circle. And remembering that we're dealing with just half a circle here, we're going to take that final answer and divide it by 2. And we end up with simply 4 pi. And there's the perimeter of our circle. Okay, I want to try one more question. And we're going to do question 15 just because. Oh, we're getting a question about canceling out of the pies. Okay, sorry. So before I go on, yes, this sometimes throws some people. So let me just talk about this for a minute. When you have two things that are exactly the same on both sides, in this case, pi, what I've done is I've just gone ahead and canceled them because we don't need them. They're not the numbers that are making our life easier. The numbers that we want to be working with are 8 and have that equivalent to our unknown. Why is it that we can just make the pi disappear? Because we're doing the same thing to both sides. So I'm going to make it go out of this context, and I'm going to show it in a different context, because this is sort of an important question, and it goes to the root of everything that we do in algebra. This symbol is incredibly useful. This, of course, is our equals sign. If I have something on one side, and I'll call it 8 pi, that means 8 times whatever pi is. And then say I had something else on the other side, like 4r pi. This also means that it's being multiplied by pi. Because I'm multiplying by pi on both sides, I am allowed to say, I'm going to divide this side by pi. As long as I follow the basic rule of whatever you do to one side of an equation, you also do to the other. Okay? If I divide by pi on the left-hand side, I have to divide by pi on the right-hand side. And when I do that, they cancel out. And that's why they disappear. And a lot of the time, rather than taking the step to show that we're dividing it, we'll just take a look at something and say, oh, these things are equivalent on both sides, and I don't need them, so I'm just going to make them disappear. And so what this would end up leaving us with is something that looks like that. Oh, and you wanted to know about that that last pi. Oh, again, the same idea, because the formula says 2 pi r, and let's say that I was dealing with this, and this was going to be the equivalent of 4, yeah, I'll go with 4 pi. It's the same idea. Because I have pi's in both places, I could divide this side by pi as long as I'm also dividing this side by pi, and those would cancel out. And then I would just be left with 2 times r is equal to 4. So hopefully for those of you who are confused by that one, that will clarify. If not, hold on to that question. I want to try and squeeze in one more question, and then I'll take questions from everybody. Okay, so we're going to take, oops, you can't see what I'm looking at. Let me try that again. We're going to try taking a look at this question here. Question number 15, find the perimeter and area of the following shape. Give both exact answers and the approximate answers rounded to 2 decimal places. So we have a shape that is mostly looking like a rectangle that somebody stuck a half circle on one side. And there's the shape. And we want to know both the perimeter and the area. So let's start to fill in all of sort of the missing pieces that we know that we've got. This side is 6. Over here I have a 1 and a 1, which take up the equivalent of this part here being a 1 and this part here being a 1, meaning the part that's missing in between must be 4. 6 minus 1 minus 1 gets us 4. And if that space is 4, that tells us that that space is 4. Remembering that if we go from one edge of a circle to the other, passing through the center, that is our diameter. What we're usually working with in circles to find out anything is we want the radius. And the radius is always half the diameter, so I know that that length there is 2. I have 2 marks on this line, 2 marks on this line, which says these things are equivalent. So if that side is 10, this side is 10. It wants the perimeter, which means we need to find the circumference of this circle. And, sorry, the circumference of this half circle. So we start off by finding the circumference of the whole circle. Circumference is, of course, 2 times pi times the radius. Our radius in this case is equal to 2. So our circumference is going to be equal to 2 times pi times 2. I'll multiply my 2's together, and it tells me that our circumference is going to be equal to 4 pi. But that's for the whole circle. I just want half of the circle, which I'll represent in this case by our circumference divided by 2. That means our 4 pi will also be divided by 2, which means ultimately we're just looking at 2 pi. So this section of our perimeter is equal to 2 pi. Having now put together all of the pieces along the outside, I can go ahead and calculate our perimeter. We add up the numbers along the outside. So I'll start here and work my way around. 10 plus 6 plus 10 plus 1 plus 2 pi plus 1, and that gets us back to the beginning. We'll add this up. 10 plus 10 is 20, plus 6 is 26, plus 1 gets me 27, plus 1 gets me 28, and then this part, the 2 pi, comes along. That's our exact answer. Remembering that pi can be approximated as 3.14, I can take my 2 pi and I can approximate it down. 2 times 3.14 is going to be approximately 6.28. So we can also say that our perimeter is equal to approximately 34.28. Okay. Next, we want to figure out our area. The area is just slightly different. I can figure out the area of my rectangle very easily. It's going to be 6 times 10. And then to figure out that, I just need half of the area of that circle. So I'm going to add 1/2. The formula for the area of a circle is pi r squared. So I'll take that pi. Our radius we already determined was 2. So I'm going to take pi times 2 squared, and we'll keep that all in brackets. We'll work out these numbers. 6 times 10 is 60. 2 squared is 4. Half of 4 is 2. So again, we're back down to 2 pi. That's our exact answer. We do the same thing as we did up here. 60 plus 6.28, and it means that our area is approximately 66.28. and that's area, so that should be in units squared. This is perimeter, so it's just in units. Okay, it's 6:25, so we're running out of time really, really quickly here. I'm sorry about that. I went a little longer than I expected. Has anybody got any questions that they're willing to ask while the whole group is here and just before I let everybody go? Okay, I had a request earlier. Someone was wondering if we could go over how to turn decimals into fractions again. Yes, absolutely. Let me pull up just a couple of quick examples of that so that we can take a look at this together. I don't seem to have any of those put out right now, so I will do this real quick. Hopefully everybody has this down. If not, it'll be on part of the recording. Okay, decimals into fractions. Let's say that we've got a decimal 0.17. The easiest way to think of it is always to count your number of decimal places. This has 2 decimal places, okay, which is to say it takes us to the 100th place. But the other easy way to think of it, if it has 2 decimal places, you're going to want a 1 followed by 2 zeros on your denominator. Okay, so this becomes 17 over 100 because that has 2 zeros. And this works no matter how many decimal places you have. You just go ahead and follow that same number of zeros. So if I had 0.1, 2, 3, 4, 5, just as a for instance, this has 5 decimal places. So it will have 5 zeros on the bottom. And that's always your first step. That's the easiest way to get to there. And then from there, you then reduce it. So let's say, for example, I had the decimal 0.24. 2 decimal places tells me I'm going to have 2 zeros, so that's going to be 24 over 100. But that reduces, and I know that that reduces because both 24 and 100 will divide by 4. And so when I do that, I end up with 6 over 25. I'm being asked to go really quickly over the repeating numbers, so let's take this same idea, but let's say now my 0.24 is repeating. It's going on and on and on and on and on. Well, now instead of putting the number of zeros, that same number of decimal places is going to be in 9s. So in this case, I'm going to get 24 over 99. And again, this is the important part that we want to remember. Once we've done that, we want to check to see if this reduces. Well, both 24 and 99 divide by 3. So when I do that, this is going to come down to 8 over 33, and that's the final number that I'm looking for. But that same idea where if you're counting, you're always counting your decimal places, and that's always what's informing you.